The night sky does not scream, it does not shout. It waits. If you stand on the high ridge of the mountain where the air is thin and cold enough to freeze the breath in your lungs, you can feel that waiting. It is a heavy velvet silence. Above the observatory, the Milky Way stretches like a spilled river of milk and diamonds, so bright and so clear that it feels like you could reach up and run your fingers through the dust of dead stars. It was November the 9th, 2025. Inside the control room, the world was defined by the soft hum of cooling fans and the rhythmic blinking of server lights. The room smelled of stale coffee and the ozone scent of heated electronics. Dr. Elias Thorne sat in his chair, the fabric worn thin from years of long nights. He rubbed his eyes, which felt dry and gritty. He was alone. In this line of work, being alone was the standard operating procedure. You, the telescope, and the infinite dark. The target for tonight was an object designated 3I Atlas. 3I stood for interstellar. It was the third visitor from outside our solar system that humanity had ever spotted. The first two had been fast, rocky, and quiet stones skipping across the cosmic pond. But Atlas was different. It had been drifting near the edge of Jupiter's orbit for weeks, moving with a strange, lazy elegance. It was not tumbling like a rock, it was gliding. Elias tapped his keyboard. On the main screen, the image from the telescope refreshed. Visually, 3I Atlas was beautiful. In the high-resolution processing, it looked like a shard of silver glass suspended in the void. It caught the distant light of the sun and reflected it with a purity that made the senses weep. It was peaceful. It looked like a lonely traveller just passing through, minding its own business in the great empty theatre of space. But on the secondary monitors, the data was telling a completely different story. It was a story of violence. "This cannot be right," Elias whispered to the empty room. His voice sounded small, swallowed by the hum of the machines. He leaned closer to the screen, squinting at the telemetry stream. The numbers were cascading down the black terminal window in green lines. They were fast, too fast. It looked like the computer was having a panic attack. The telescope was measuring the light coming off the object. By measuring the light, astronomers could calculate the size of the object. It is a simple rule of physics: a larger surface reflects more light. If you know how far away something is, and you know how bright it is, you can figure out how big it is. Elias ran the script again. System check normal, sensor calibration perfect, distance 500 million kilometers. He looked at the result. He blinked, thinking perhaps his tired eyes were playing tricks on him. He took a sip of cold coffee and looked again. The numbers hadn't changed. According to the visual sensors, the actual picture of the object, Atlas, was a splinter of rock roughly 2 kilometers long and half a kilometer wide. It was a respectable size, but nothing monstrous. It was a small island in a sea of nothingness. However, the light data disagreed. The amount of sunlight bouncing off Atlas suggested it was massive. The brightness readings were off the charts. For an object to reflect that much light, it would need a surface area immense enough to cover a small country. Elias pulled up a fresh command line. "Calculate surface area discrepancy," he typed. The computer processed for a moment, the cursor blinking a rhythmic heartbeat. Then the result appeared. Discrepancy factor 16.0. Elias sat back, the leather of his chair creaking loudly in the quiet room. This was the surface area problem. In simple terms, it was a physical impossibility. Imagine holding a standard playing card in your hand. You can see it. You can measure it with a ruler. It is small. But now imagine that when you shine a flashlight on that playing card, it reflects as much light as a giant billboard. That was what 3I Atlas was doing. Physically, it was small. Mathematically, it was gigantic. 16 times, Elias muttered. It has 16 times more surface area than its physical shape allows. He stood up and walked to the large window overlooking the telescope dish outside. The dish was a white ghost in the moonlight, pointed silently toward Jupiter. The wind was picking up outside, a low whistle against the reinforced glass, but Elias hardly heard it. A discrepancy of 16 times was not a margin of error. A margin of error is 1%, maybe 2. 16 times was a different reality. It meant that the object was somehow folding space. Or perhaps that the surface of the object was not smooth glass, but something infinitely complex, like a piece of paper crumpled into a tight ball, hiding its true size in thousands of microscopic wrinkles. But even that didn't make sense. To get a factor of 16, the wrinkles would have to be fractal, folding in on themselves down to the atomic level. Or there was the other theory, the one astronomers didn't like to say out loud because it sounded less like science and more like a ghost story. Maybe the object wasn't reflecting light. Maybe it was emitting it. But 3I Atlas was cold. The thermal sensors showed it was freezing, matching the deep cold of space. It wasn't a star, it wasn't burning, it was just wrong. Elias returned to his desk. The beauty of the image on the main screen now felt deceptive. That silver shard wasn't just a rock, it was a mask. He began to type a message to the Central Bureau in Massachusetts. Usually he would wait, he would triple check, he would sleep on it and look again in the morning with fresh eyes. But the feeling in his gut was heavy like a stone-swallowed whole. This wasn't a glitch. The data was too clean, too consistent. Subject 3 I Atlas, photometric anomaly, urgent. He paused his finger hovering over the keys. On the screen, the data stream suddenly shifted. A new set of numbers appeared at the bottom of the list. Rotation period changing. Elias frowned. Objects in space spin. They have a rhythm, a heartbeat. Atlas had been spinning once every 8 hours. A slow, lazy tumble. But now the numbers showed it was slowing down. 0.05% slower, then 0.1%. It wasn't just drifting anymore. Something was applying the brakes. In the absolute vacuum of space, there is no air to slow you down. There is no friction. An object only slows down if a force acts upon it. Gravity, a collision, or intent. The silence of the mountain suddenly felt very loud. The static beauty of the universe, the comforting, predictable clockwork of the stars seemed to fracture. Elias looked at the silver shard on the screen. The November paradox had begun. The universe was no longer just a place of silent dead rocks. The math was broken. The numbers were screaming that something impossible was sitting out there in the dark watching Jupiter, and it was bigger on the inside than it was on the outside. He finished typing his message. He didn't use technical jargon. He didn't use the complex codes for luminosity or geometric albedo. He just wrote what the universe was telling him. Message, it is waking up. And the math says it is bigger than it looks, much bigger. He hit send. Outside the wind died down. The night sky remained perfectly still, a tapestry of ancient light. But to Elias, looking up through the glass, the stars no longer looked like diamonds. They looked like eyes. And for the first time in his career, the silence didn't feel peaceful. It felt like a held breath. It was July 2025. Looking back from where we are now, that summer feels like a different lifetime. The world was loud, filled with the usual noise of politics and heat waves, but looking up the sky was keeping a secret. We did not know yet how strange things would become. We only had the math, the orbital mechanics, and the old reliable glass eye floating above our heads. We turned to the Hubble Space Telescope. You might wonder why we relied on Hubble. By 2025, the James Webb Space Telescope had been the superstar for years, capturing galaxies from the dawn of time. But Webb looks at the universe in infrared heat vision. To see 3I Atlas as it truly was, to understand its physical shape before it got too close to the sun, we needed visible light. We needed to see it the way a human eye would see it if a human eye could see perfectly in the dark. We needed the old guard. There is something comforting about Hubble. It has been up there since the 1990s. It has seen comets crash into Jupiter. It has watched stars die and be born. It is steady. It is solid. When the panic started to rise later, I often thought back to those quiet data streams from July. Hubble did not panic. It just stared into the blackness and counted the photons. This brings us to the heart of the problem. How do you measure the size of a rock that is millions of kilometers away, floating in total darkness against a background of infinite black? You cannot walk up to it with a measuring tape. You cannot use radar yet because it is too far away. We use a method called photometry. To understand photometry, imagine you are standing in the middle of a massive pitch-black football stadium at night. You know there is a person holding a light somewhere in the stands, but you cannot see the person. You can only see the light. If that light is very bright, you might assume the person is holding a massive spotlight. If the light is dim, you might assume they are holding a tiny candle. But there is a trick. A massive spotlight effectively looks like a tiny candle if it is 5 kilometers away. Conversely, a tiny candle looks like a massive spotlight if it is right in front of your face. To know the size of the light source, you must know exactly how far away it is. With 3I Atlas, we knew the distance perfectly. The laws of gravity do not lie. We knew exactly where it was in the solar system. So when Hubble turned its mirror toward that specific patch of empty space, we were not guessing the distance. We were measuring the candle. Hubble opened its shutter. It acted like a rain bucket, but instead of catching water, it caught particles of light photons. We counted them, one by one. The computer tallied them up to give us a brightness value which astronomers call magnitude. But there is a second trick to photometry, and this is where the ground truth of July 2025 comes from. It is the problem of the surface. Imagine you have 2 balls of the exact same size, let's say 1 meter wide. One ball is made of polished silver, the other is made of black charcoal. If you shine a light on them, the silver ball will look brilliant and bright. The charcoal ball will be almost invisible. If you only measure the brightness, you might think the charcoal ball is tiny or the silver ball is huge. This reflectivity is called albedo. For a long time, we assumed comets were somewhat shiny, dirty snowballs, but decades of space missions taught us the truth. Comets are dark. They are incredibly dark. They are darker than fresh asphalt on a road. They reflect only about 4% of the sunlight that hits them. They are the color of coal. So, July 20 to 25, we took the brightness Hubble saw, and we applied the math of the dark object. We assumed 3i Atlas was dark, like a typical comet nucleus. We plugged the numbers into the equation, the distance, the brightness, and the darkness of the surface. The calculation churned out a number. It was not a range, it was a solid singular definition of reality at that moment. 5.6 kilometers. That was the diameter. It was not a planet killer the size of a city, but it was substantial. It was a mountain floating in the void. This measurement was our anchor. It was our ground truth. No matter what happened later, no matter how the data twisted or how the tail behaved, we knew that in the quiet vacuum of July, the solid core of this object was roughly 5.5 kilometers wide. This is where the story begins to diverge from the normal rhythm of astronomy. If 3i Atlas had been a normal comet, the image from Hubble would have looked fuzzy. A normal comet, even far out in the solar system, usually begins to wake up as it feels the distant warmth of the sun. The ice on its surface sublimates, it turns directly from solid ice to gas. This creates a cloud of gas and dust around the nucleus called a coma. When you look at a normal comet through a telescope, you do not see the rock. You see the cloud. It looks like a soft, glowing cotton ball. The coma makes the comet look huge, sometimes hundreds of thousands of kilometers wide, masking the tiny rock inside. But the Hubble images from July were different. They were hauntingly sharp. 3i Atlas was a pinprick, a singular hard point of light. There was no fuzz, there was no cotton ball, there was no coma. This was the first warning that something was wrong, though we interpreted it as scientific curiosity at the time. Why was it so naked? Usually a comet without a coma means one of two things. Either it is a dead comet, a rock that has gone around the sun so many times that all its ice has melted away, leaving just a husk. Or it is a rock made of something that does not melt easily, something harder, something more stubborn than ice. We looked at the data from Hubble, and we felt a sense of solidity. We thought we understood it. We said, okay, it is a 5.6 kilometer inert nucleus, it is just a dark rock passing through. We were comfortable with that answer. It fit the physics, it fit the photometry, it made sense. The light curve, the graph showing how the brightness changed over time, was flat and steady. A normal comet flickers as it rotates, exposing icy patches and dusty patches. 3i Atlas just shone with a dull, constant grey light. It felt heavy. It felt mechanical in its consistency, though we did not use that word yet. In those quiet days of July before the breaking news alerts and the global arguments, we had this beautiful, clean data set. We had the distance, we had the light, we had the size. 5.6 kilometers. We held on to that number like a raft. We trusted the process. We trusted the albedo corrections. We trusted Hubble. We thought we had measured the guest at our door, and we thought we knew exactly what walked out of the dark. But looking back, the lack of a coma should have bothered us more. The silence of the object should have been louder. We were measuring the reflection of the sun off its back, thinking we were measuring a piece of ancient ice. We were right about the size. 5.6 kilometers was real. The object was there. It was solid. But we were wrong about what was doing the reflecting. As the calendar creeps toward October 30th, the vast silent emptiness of space begins to change. We are no longer in the realm of deep shadows. We are entering the kingdom of light. The comet, a traveller from the frozen edges of existence, begins to feel a sensation it has not known for thousands of years: warmth. This is the journey to perihelion. In simple terms, perihelion is the point in the orbit where an object comes closest to the var. It is the moment of truth, the climax of the journey, and the ultimate test of survival. For our icy traveller, this approach is not just a movement through distance. It is a transformation of its very soul. The closer it gets, the more the sun dominates the sky, growing from a bright star into a burning golden giant that fills the view. The temperature begins to climb slowly at first, and then, with increasing intensity, the absolute zero of deep space is replaced by a searing heat, a thermal embrace that seeks to wake the sleeping giant. Deep inside the comet, beneath the dark dusty crust, something magical begins to happen. For eons, the materials inside this celestial mountain have been locked in a deep sleep. These are not rocks as we know them on Earth. They are frozen gases, ancient ices preserved from the very birth of our solar system. The most important among them are water ice and frozen carbon dioxide. On Earth, we know carbon dioxide as an invisible gas that we breathe out. But out here in the extreme cold, it is a hard, solid, rigid, and unmoving. However, the sun changes everything. As the heat penetrates the surface of the comet, it does not cause the ice to melt into a liquid like an ice cube on a kitchen counter. In the vacuum of space, liquid water cannot exist in the open. Instead, a rare and beautiful physical process takes place. It is called sublimation. Sublimation is the direct leap from a solid state to a gas state, skipping the liquid phase entirely. Imagine a block of dry ice on a stage. It does not leave a puddle of water, but rather disappears into a thick white mist. This is exactly what happens to the comet, but on a scale that is almost impossible to comprehend. The frozen carbon dioxide and water ice touched by the solar fire instantly turn into vapor. They expand violently, taking up much more space as a gas than they did as a solid. This process is the breath of the universe. It is a slow, rhythmic exhalation. As the heat intensifies, the pressure builds up underneath the dark crust of the comet. This gas needs to escape. It pushes against the surface, finding weak spots, cracks, and fissures in the rock. And then, with a silent release of power, the surface bursts open. This is not an explosion of destruction, but an explosion of creation. From these cracks, great geysers of gas and dust shoot out into the void. These are called jets. They are not like the water fountains we see in a park. These jets are colossal. They can shoot material hundreds, sometimes thousands of kilometers into space. They are powerful streams of matter carrying with them the ancient dust that has been trapped in the ice since the dawn of time. Visualize these jets. They are like long white fingers reaching out to touch the stars. In the golden light of the sun, they glow with a ghostly brilliance. They twist and turn, dancing in the vacuum. As the comet rotates, these jets spin like the beams of a lighthouse, sweeping across the darkness. It is a magnificent display of physics and beauty intertwined. The comet is no longer just a rock. It has become a dynamic living thing, breathing out the essence of its history. The dust and gas released by these jets do not just disappear. They are caught by the solar wind, a stream of charged particles flowing constantly from the sun. This wind pushes against the gas and dust, blowing it back behind the comet. This is how the tail is formed. It is a glorious train of light, a veil of sparkling dust that stretches for millions of kilometers. It is a banner that announces the comet's arrival to the entire solar system. To watch this process is to watch a dance of fire and ice. The fire is the sun, relentless and overwhelming, pouring energy into the system. The ice is the comet, fragile yet resilient, responding to the heat by transforming itself. It is a delicate balance. If the heat is too little, the comet remains asleep, a dark rock invisible to the eye. If the heat is too much, the sublimation becomes too violent and the comet could tear itself apart. But right now, in this build-up to the 30th of October, the balance is holding. The feeling is one of grandeur. It is slow-motion destruction that creates beauty. Every second, tons of material are being lost, stripped away from the nucleus and cast into the void. The comet is sacrificing its own body to create the spectacular display we see from Earth. It is shedding its skin layer by layer in the warm bath of solar radiation. Think of the molecules of carbon dioxide. For billions of years, they were locked in a crystal prison, unable to move, frozen in the dark. Now suddenly they are free. They are energized. They rush outward, expanding into the vastness of the solar system, catching the sunlight and scattering it in all directions. It is a liberation. The sublimation is not just a scientific term. It carries the meaning of ascending, of rising up to a higher state of being. The matter is being elevated from the heavy grounded solid into the ethereal flying gas. The structure of these jets creates a texture in the space around the comet. It looks like the petals of a cosmic flower opening up to the morning sun. The light plays through the dust, creating shadows and rays that shift and change. It is a fluid sculpture, constantly being remade by the energy of the sun. The sheer size of this structure is humbling. The cloud of gas surrounding the comet, called the coma, can grow to be larger than the planet Jupiter, and the tail can stretch longer than the distance between the Earth and the Moon. Yet it all comes from a nucleus that might be only a few kilometers wide. This is the magic of the solar system. A tiny frozen heart can create a spectacle that spans the heavens. As we approach the perihelion point, the dance accelerates. The sublimation becomes more intense. The jets grow stronger, brighter, and more numerous. The comet is singing its song of ice and fire, a silent melody that vibrates through the solar wind. It is a moment of pure physical poetry, warm, magnificent, and profoundly alive. The universe is breathing, and for a brief moment we are close enough to feel its breath on our faces, illuminated by the brilliant, life-giving light of our star. As the distance closes, the intensity of the light becomes nearly blinding. The sun is no longer a distant friend, it is a roaring furnace. The surface of the comet is now a chaotic landscape of shifting shadows and blinding white steam. The Thanghua process reaches its peak. The carbon dioxide ice, which is more volatile than water ice, drives the activity furiously. It bursts forth, dragging the heavier water molecules and dust particles with it. It is a symphony of chemistry and physics playing out in the silence of the void. We must appreciate the slowness of this drama. To our eyes, a comet looks like a static painting in the night sky. It hangs there motionless among the stars. But this stillness is an illusion caused by the vast distances of space. In reality, the comet is hurtling through space at speeds that would boggle the mind tens of thousands of kilometers per hour, and the internal changes are constant. The jets are evolving, shifting their direction as the sun warms different faces of the rotating nucleus. It is a performance that takes place over days and weeks, a slow-burning reveal of nature's power. The dance of fire and ice is the perfect metaphor. Fire represents the active, energetic masculine force of the sun. Ice represents the passive, dormant, feminine potential of the comet. When they meet, life in the form of activity and motion is born. This interaction is the heartbeat of our solar system. Without the sun's warmth, the comet is just a dead rock. Without the comet's ice, the sun has nothing to illuminate, nothing to bring to life in the empty dark. They need each other to create this spectacle. On October 30th, this relationship reaches its most intimate moment. The heat will be at its maximum. The stress on the comet's body will be immense. Gravity will pull at it, trying to tear it apart, while the internal pressure of the sublimation pushes outward, trying to explode it. It is a majestic struggle. Will the comet survive? Will it hold itself together against the tidal forces and the thermal shock? Or will it crumble into a stream of debris, a ghost of what it once was? For now, we simply watch the breath of the universe. We watch the white mist rise. We watch the tail grow longer and brighter, painting a stroke of white ink across the black canvas of space. We feel the warmth of the narrative, the awe of the scale, and the simple beauty of a solid turning into a gas, freeing itself from the chains of gravity to fly among the stars. It is a time of anticipation, a time of wonder, and a time to look up and witness the magnificent mechanics of the cosmos in action. The universe as a strict accountant. When we look up at the stars, we often see mystery, romance, and wonder. But to a physicist like Avi-Loeb, the universe is, at its core, a strict accountant. It operates on a ledger that must always balance. There is no such thing as a free lunch in astrophysics. Every action has a cost, and that cost is usually paid in energy. This brings us to the most fascinating and perhaps the most damning chapter of the Oumuamua saga, the energy balance. To understand why Oumuamua was so strange, we have to stop looking at it as a rock and start looking at it as a physical system, a machine that consumes fuel to move. The scientific debate surrounding this object was not just about what it looked like in a photograph. It was a battle of mathematics. And when Avi-Loeb sat down to check the receipts, the numbers simply did not add up. The solar budget. Let us begin with the income in our equation, sunlight. When an object travels through our solar system, the sun acts as its only source of power. Sunlight strikes the surface of the object, warming it up. If the object is a comet, this heat causes the ice on its surface to turn directly into gas, a process called sublimation. This gas shoots out into the vacuum of space. According to Newton's laws of motion, this shooting gas acts like a rocket thruster that pushes the object forward. This is the mechanism behind the non-gravitational acceleration we discussed earlier. However, the sun is not an infinite battery. It provides a very specific, calculable amount of energy per square meter. We know exactly how much solar energy was available to Oumuamua at its distance from the sun. This is a fixed number. It is the allowance the object had to spend. The cost of moving. Now let us look at the expense mass loss. To push a heavy object, you need a strong force. To get a strong force from evaporating gas, you need to burn a lot of fuel. You need to evaporate a massive amount of water ice to generate enough thrust to push a mountain-sized rock through space. This is where the logic begins to tighten its grip. Critics of Loeb attempted to explain away the anomaly by suggesting the dark comet theory. They argued that Oumuamua was indeed a comet, but one made of very pure water ice without any dust. They claimed this purity was why we did not see a tail. They argued the tail was there, but it was transparent and invisible to our telescopes. But Loeb looked at the energy required to make this happen. To achieve the extra speed that astronomers observed to push Oumuamua that hard, the object would have needed to evaporate a tremendous amount of its own mass. The great contradiction, 23 kilometers versus 56 kilometers. This leads us to the most critical calculation, the moment where the natural explanation begins to fracture. In an attempt to make the natural comet theory work, a team of reputable astronomers published a paper. They calculated the physics of a pure ice comet. They suggested that for Oumuamua to behave the way it did without falling apart and to maintain its rotation, it must have been a large fluffy object. They calculated that to maintain its spin and stability while evaporating that much gas, the object needed to be roughly 23 kilometers, about 14 miles in diameter. Let us visualize that. That is a massive object. It is a mountain floating in space. It is bigger than the city of Manhattan. However, there was a fatal flaw in this argument. We have telescopes. We have eyes on the sky. We measured how much sunlight Oumuamua reflected. Based on its brightness or lack thereof, the object appeared to be very small. If Oumuamua were a typical comet or asteroid, its observed brightness suggested it was only about 5.6 kilometers, about 3.5 miles wide at the very most. In reality, it was likely much smaller, perhaps even the size of a football field. The impossible equation. Here is the trap that logic sets for the natural explanation. First, consider if the object was huge, 23 kilometers. If it were this big, it would have enough surface area to catch a lot of sunlight. However, a 3-kilometer object is incredibly heavy. The rocket engine of evaporating gas would need to be enormously powerful to push such a heavy beast. But more importantly, a 23-kilometer ball of ice reflects a lot of light. It would have shone brightly in our telescopes like a beacon. We did not see this. The object was dim. Second, consider if the object was small, 5.6 kilometers or less. This matches the dimness we observed. But a small object has very little surface area. It cannot catch enough sunlight to power the massive rocket thrust needed to move a rock. Furthermore, if a small object evaporated enough gas to generate that speed, it would lose more than 10% of its total mass in a very short time. This rapid weight loss creates a new problem, the spin. Imagine a spinning figure skater. If she suddenly loses 10% of her body weight, her spin changes dramatically. If a comet shoots out jets of gas violently enough to accelerate it, usually causes the object to wobble uncontrollably or spin up until it tears itself apart. We did not see this either. Oumuamua's spin remained smooth and steady, repeating perfectly every 8 hours, breaking the laws of Near. Avi Loeb's calculation revealed a discrepancy that could not be ignored. Imagine you see a large truck moving down the highway at high speed. You know how heavy a truck is. You know how much horsepower is needed to move it. Now imagine you look under the hood and find a tiny lawnmower engine. The laws of physics say that the lawnmower engine cannot move the truck at that speed. It is energetically impossible. This is the situation with Oumuamua. The dark comet theory required the object to be massive to explain why it didn't spin out of control, but it required the object to be invisible to explain why we couldn't see it. It required the sun to deliver more energy than is physically available at that distance. The only variable left. When you eliminate the impossible, whatever remains, however improbable, must be the truth. The energy balance calculation suggests that Oumuamua could not be a thick, heavy chunk of rock or ice. There is only one way to balance this equation. For the small amount of sunlight energy available to produce such a strong push acceleration, the object must be incredibly light. It cannot be a solid rock. It must have a mass that is tiny compared to its surface area. It must be thin. If the object is thinner than anything found in nature, perhaps only a few millimeters thick, then the pressure of sunlight alone is enough to push it. You do not need gas. You do not need evaporation. You do not need a tail. You simply need sunlight bouncing off a surface. In the ledger of the universe, a light sail is the only item that balances the budget. It explains the acceleration. It explains the lack of a tail. It explains the stability. The numbers do not lie. The narrative of a natural comet requires us to believe in a phantom object, one that is huge, but invisible, heavy, but powered by a weak engine. The narrative of the artificial object only requires us to accept that perhaps we are not the only ones building things in the Milky Way. As we drift deeper into the heart of this celestial masterpiece, we move beyond the general shape and begin to witness the violent, beautiful machinery that constructs the nebula. When we look through the lens of the Hubble telescope, we are not just looking at a painting, we are looking at a frozen explosion, a storm of unimaginable proportions. Here we encounter the architecture of the winds, a complex system of fluids and gases that defies the emptiness of the void. The first thing that captures our awe is the presence of the jets. In this specific cosmic theatre, we can identify at least 7 distinct streams of flow. These are not gentle breezes, they are powerful collimated beams of matter, shooting out from the dying star like arrows fired from a galactic bow. Why are there 7? Why not a perfect circle? This reveals the profoundest symmetry of the universe. While we often imagine stars and planets as perfect spheres, the death of a star is rarely a symmetrical event. It is messy, chaotic, and wonderfully imperfect. These jets suggest that the central star did not expel its layers evenly. Perhaps it was spinning wildly, wobbling on its axis, or perhaps it was influenced by the gravity of a hidden companion star. Whatever the cause, these 7 distinct fingers of gas stretch out into the darkness, breaking the pattern of the main ring. They act as highways for matter transporting gas from the hot centre to the cold outer edges of the system. This brings us to one of the most fascinating concepts in stellar physics, the idea of the solar wind acting as a brake. To understand this, we must imagine the history of the star. Thousands of years ago, when the star was a red giant, it breathed out a slow, lazy wind. This gas drifted away gently, moving at a relatively low speed. But now the core is exposed. It is a white dwarf, hot and angry, screaming out a new wind that travels at terrifying speeds millions of kilometers per hour. What happens when this new fast wind catches up to the old slow wind? It slams into it. It is exactly like a speeding race car crashing into the back of a heavy, slow-moving truck. The fast wind cannot just pass through, it hits a wall of resistance. This interaction acts as a cosmic brake. The energy of that collision has to go somewhere, and it is converted into heat and shock waves. This is what sculpts the nebula. The beautiful glowing rim we see is actually a crash site, a zone of turbulence where the fast wind is being forced to slow down, piling up material like a snowplow pushing through a drift. If we could shrink ourselves down to the size of an atom and float inside these winds, the scene would be terrifyingly majestic. This is where we must visualize the velocity of the gas molecules. In our daily life, air moves relatively slowly, but here the temperature is the measure of speed. In the hottest parts of these jets, the temperature creates a frenzy of motion. We are talking about velocities that defy common sense. Imagine a single proton, the nucleus of a hydrogen atom. In this superheated environment, it is not floating, it is racing. It moves at speeds of hundreds of kilometers per second. In the vast emptiness of space, usually a particle can travel for light years without hitting anything. But inside these jets, the gas is dense enough that collisions are inevitable. Picture this: 2 protons traveling at supersonic speeds rushing toward each other in the vacuum. They collide with tremendous force. This is not a quiet bump, it is a violent transfer of kinetic energy. When they smash together, the energy shakes the electrons, exciting them to higher levels. When those electrons calm down and return to their original state, they release that energy as a tiny packet of light, a photon. Now multiply that single collision by trillions upon trillions of times every second. That is what creates the glow. The light of the nebula is the visible echo of countless microscopic car crashes happening in the dark. It is a symphony of atomic violence that results in the peaceful glowing light that travels across the galaxy to reach our eyes. One might ask, how can these structures exist for so long? On Earth, a gust of wind lasts only a moment. A storm might last a few days, yet these jets and cometary knots persist for months, years, even centuries. To us, they look like a still photograph frozen in time. But this is an illusion caused by the sheer scale of the structure. The reason they last so long is due to the immense distances involved and the lack of friction in the traditional sense. Once a stream of gas is set in motion in the vacuum of space, there is very little to stop it. It carries the momentum of a titan. Furthermore, the distances they must travel are so vast, trillions of kilometers, that even moving at lightning speeds, it takes years to cover any noticeable distance from our perspective on Earth. We are watching a slow-motion movie. If we could watch this nebula for 500 years, we might see the jets expand, slightly pushing further into the dark. But in the short span of a human lifetime, they appear as eternal monuments. They are stable because they are driven by the relentless pressure of the central star, a power source that does not run out of fuel quickly. It is a humbling realization. The spokes of this great wheel, the knots that look like comets, and the turbulent winds are all part of a dynamic flowing river of light. They tell us that space is not empty and silent. It is alive with energy. It is a place where the death of a star creates a complex, structured and enduring legacy. The solar winds are not just blowing gas away, they are sculpting a masterpiece using pressure and velocity as their chisel. As we observe the 7 jets and the braking mechanism of the winds, We are witnessing the universe seeking balance. The fast meets the slow, the hot meets the cold, and in that struggle beauty is born. It is a reminder that even in the destruction of a solar system there is order, structure, and a magnificence that commands our absolute silence and respect. As we drift closer to the heart of the solar system, the silence of space betrays the violence occurring right in front of us. We often look at a comet and see a beautiful glowing brushstroke against the night stars. We see a painting. But if we look closer with the eyes of a scientist and the heart of an observer, we do not see a painting. We see a wound. We see a heavy, tragic sacrifice. This brings us to the most shocking realization of our journey, the great loss. To understand the life of Comet Halley, we must first confront the sheer violence of the Sun. As the comet rushes toward the center of our system, the heat rises drastically. The surface, which has been sleeping in the frozen dark for decades, suddenly screams into action. The ice does not just melt into water, it explodes directly into gas. It tears itself apart to escape the heat. This process creates the magnificent tail that we admire from Earth. But that tail is not just light, it is matter. It is the physical body of the comet ripping away and leaving forever. Let us look at the numbers, for they are truly terrifying. When Comet Halley is at its most active, when it is feeling the full power of the solar wind, it does not just lose a few buckets of ice, it does not just lose a layer of dust. Scientists estimate that during this peak time, the comet ejects approximately 5 billion tons of material into the black void of space. 5 billion tons! It is a number so large that it becomes meaningless to the human mind. We hear billion tons, and we nod, but we do not truly see it. So let us try to visualize this weight. Let us try to hold this loss in our minds. Imagine a large commercial airplane like a Boeing 747. These are massive machines, heavy giants of the sky that weigh hundreds of tons. Now imagine filling the entire sky with them. To match the weight that Comet Halley loses in just one single month, you would need millions of these heavy airplanes. Now imagine taking all those millions of airplanes and simply throwing them into a furnace. Imagine watching them turn to ash and smoke, vanishing completely. That is the scale of the destruction. It is a graveyard of matter created every single month. If airplanes are too hard to picture, let us look at the ocean. Imagine a vast lake, deep and wide. Imagine scooping up 5 billion tons of water. That is enough water to drain a small sea. Now imagine that entire sea evaporating into steam and disappearing into the sky, never to return. This is not happening over 1,000 years. This is not happening over a century. This is the price the comet pays every single month when it is near the sun. It is a hemorrhage. It is a cosmic bleeding that is almost impossible to comprehend. This leads us to a very dark and heavy realization. If you lose 5 billion tons of yourself, what is left? How much of you remains? We know that the total mass of Comet Halley, the entire weight of this potato-shaped mountain of ice and rock, is estimated to be around 33 billion tons. Pause for a moment and do the math with me. The total body is 33 billion tons. The loss during the peak of the heat is 5 billion tons per month. When you look at those two numbers side by side, a feeling of dread begins to settle in. It feels like a mathematical impossibility. It feels like a sentence of death. If you possess $33 and someone takes $5 from you every minute, you will be bankrupt before you finish your coffee. So we must ask the question that hangs heavy in the vacuum of space. Can a star really bleed this much without vanishing instantly? How is Halley still here? How has it returned to us again and again for thousands of years, recorded by Babylonian astronomers, by Chinese scholars, by medieval monks? If it bleeds 5 billion tons a month, surely it should have dissolved into a ghost long ago. The answer lies in the darkness. The saving grace for Comet Halley is that it does not stay near the sun. This violent bleeding is a seasonal event. For the vast majority of its 76-year orbit, Halley is far away out in the freezing depths beyond the planet Neptune. Out there it is cold, it is safe, the bleeding stops, the ice hardens, the comet sleeps like a bear hibernating through a long dark winter. It only loses this mass when it comes to visit us. It only suffers this great loss when it enters the inner solar system to put on its show. But this does not change the ultimate truth. It only delays it. Every time Halley swings by Earth, it is smaller than the time before. When your grandparents saw it, it was larger. When you see it, it has diminished. When your grandchildren see it, it will be a shadow of its former self. It is like a bar of soap used in the shower. It survives for a long time, but every use washes a layer away. Eventually, there will be nothing left to hold. This is the tragedy of the comet. Its beauty is its death. The glorious tail that stretches across the heavens, the white stream that inspires poets and frightens kings, is actually the comet dying. We are clapping for a funeral procession. We are admiring the debris of a crumbling world. So as we look at this object floating there with its total mass of 33 billion tons, we must look at it with a sense of overwhelming awe mixed with sadness. It is a giant yes. 33 billion tons is a mountain. But against the fires of the sun, even a mountain is fragile. It teaches us that nothing in this universe is permanent. Even the celestial wanderers, the great travellers of the sky, are slowly eroding. They are paying a toll in dust and gas for every journey they make around the star. 5 billion tons lost, gone forever into the dark. The comet continues its path lighter scarred and silent, carrying the memory of what it used to be, rushing back toward the safety of the cold, dark outer rim, hoping to survive just one more trip. To understand the first major hypothesis for our mysterious visitor, we must look backward before we look forward. We must travel back in time to the summer of 1994. We need to talk about a ghost. This is not a ghost of a person, but the ghost of a comet. Its name was Shoemaker-Levy 9. Its story provides the most compelling natural evidence for what might be happening with our current mystery object. This is the story of fragmentation. In the history of astronomy, there are moments that divide time into before and after. The collision of Shoemaker-Levy 9 with the planet Jupiter was one of those moments. Before this event, we believed that the solar system was a relatively quiet place. We thought that giant collisions were things that happened billions of years ago in the ancient past, not something that happened while we were watching. But the universe is violent, and gravity is a sculptor that works with a heavy hand. The story begins quietly at the Palomar Observatory in California. It was March 1993. 3 astronomers, Carolyn Shoemaker, Eugene Shoemaker, and David Levy, were scanning the night sky. They were looking for comets, the dirty snowballs of the solar system. They found something, but it did not look like a normal comet. Usually a comet looks like a single bright spot with a fuzzy tail. This object was different. It looked like a smear. It looked like a squashed bar of light. When the Hubble Space Telescope turned its giant eye toward this object, it revealed something breathtaking. It was not one rock. It was a line of roughly 21 separate fragments marching in a perfect row through the darkness of space. The astronomers called it a string of pearls. It was hauntingly beautiful. But how did it happen? Why was a comet broken into a perfect line? The answer lies in the invisible crushing power of tidal forces. To understand tidal forces, you do not need complex mathematics. You only need to understand that gravity depends on distance. The closer you are to a massive object, the stronger the gravity pulls you. Imagine you are falling feet first toward a giant planet like Jupiter. Your feet are slightly closer to the center of the planet than your head is. Because gravity gets stronger as you get closer, the planet pulls on your feet harder than it pulls on your head. If the planet is small like Earth, you do not feel this difference. But if the gravity is extreme, that difference becomes dangerous. The planet is effectively stretching you. It is pulling your bottom half away from your top half. If you get too close past a specific invisible line called the Roche limit, the force holding your body together is not strong enough to resist the stretching. You would be pulled apart. This is exactly what happened to Shoemaker-Levy 9. In 1992, 2 years before the collision, the comet had swung too close to Jupiter. It passed within the danger zone. The immense gravity of the gas giant grabbed the comet. It pulled the side facing the planet much harder than the side facing away. The comet, which was just a loose collection of rock and ice held together by its own weak gravity, stood no chance. It was ripped apart, it was shattered into pieces, but because of the momentum, the pieces did not just fly away in all directions. They drifted apart slowly along the path of the orbit, creating that famous string of pearls. This brings us to the dramatic climax of 1994. The entire world watched as these pearls slammed into the atmosphere of Jupiter. They hit the planet with the force of hundreds of millions of tons of TNT. The impacts were terrifying. They created fireballs larger than the Earth itself. They left dark, bruised scars in Jupiter's clouds that remained visible for months. It proved that planets can destroy comets long before they actually hit the surface. It proved that gravity can turn a solid object into a cloud of debris. So how does this ghost story explain our current mystery? Let us return to the anomaly we are studying today. We have an object that is accelerating. It is being pushed away from the sun. We calculated that for sunlight to push a rock this heavy, the rock would need to be impossibly thin like a sheet of paper. This is the surface area problem. A solid rock does not have enough surface area to catch enough wind from the sun. But what if the object is not a solid rock? What if we are looking at another string of pearls? This is the fragmentation hypothesis. It suggests that our mystery visitor is not a spaceship and it is not a solid cigar-shaped rock. Instead, it is a cloud. It might be a comet that was ripped apart by the tidal forces of its own home star before it was kicked out into the galaxy. Or perhaps it was ripped apart by our sun when it arrived. Think about the physics of a cloud of dust or a cluster of broken rocks. If you take a solid rock and smash it into dust, you do not change the total mass. It still weighs the same. However, you drastically increase its surface area. A single block of wood has a small surface area. Turn that block into sawdust and the surface area becomes enormous. If our mystery object is actually a cloud of dust and small fragments, a ghost of a dead comet, then the sunlight has millions of tiny surfaces to push against. The pressure of the solar radiation would be incredibly effective. It would push the entire cloud violently away from the sun. This would perfectly explain the extra acceleration that confused the scientists. It would explain why the object moved as if it had an engine. The engine was just the sun pushing against a cloud of wreckage. This theory also explains why we did not see a tail. Usually comets have tails made of gas, but if this object was a dry fragment, a skeleton of a rock that had been baked by radiation for millions of years, it would have no gas left. It would just be dust and gravel. When we look at the data, the string of pearls model fits the numbers surprisingly well. It solves the problem of the geometry. We do not need to imagine a perfect unnatural sheet of metal. We only need to imagine a pile of rubble. It is a tragic yet elegant solution. It suggests that the visitor was dying as it passed us. It was not a probe sent to watch us. It was a corpse. It was the remains of a planetary system far away, torn apart by gravity, drifting through the void until it passed our sun. The ghost of Shoemaker Levy 9 teaches us that looks can be deceiving. What looks like a point of light might be a cluster. What looks like a solid object might be a broken chain. The tidal forces that created the scars on Jupiter are the same forces that might have created our mystery visitor. It turns the strange acceleration from a sign of alien technology into a sign of natural violence. It reminds us that space is not just empty, it is a grinder. It chews up worlds and spits out dust. However, even this ghost theory has its own problems. If it were a cloud of dust, would it have survived the long journey between stars? Would the cloud not have dispersed and faded away into nothingness over thousands of years? The debate was not over. But for a moment, the image of the string of pearls gave scientists a way to sleep at night, believing that perhaps the laws of nature were safe, and we were alone in the dark once again. In the vast, silent cathedral of deep space, gravity is supposed to be the only law that matters. It is the great conductor moving planets and stars in a predictable rhythmic dance. For centuries, astronomers have relied on this certainty. If you know the mass of the sun and the speed of an object, you can predict exactly where that object will be 10 years from now, down to the meter. It is a clockwork universe. But 3i Atlas has stopped following the rules. As we analysed the stream of data returning from our deep space sensors, a feeling of unease began to settle over the control room. It started as a small error in the math, a tiny discrepancy between where the object should be and where it actually was. At first, we thought it was a glitch in the sensors, or a mistake in the calculation, but the error grew. 3i Atlas was moving faster than the gravity of the sun could explain. It was deviating from its calculated path. In the sterile language of astrophysics, we call this non-gravitational acceleration. But in the quiet of the observatory, it felt like something else entirely. It felt like the object was making a choice. To understand why this is so disturbing, we must look at the history of interstellar visitors, specifically the first one, Oumuamua. When Oumuamua passed through our solar system years ago, it shocked the world. It was a long, cigar-shaped rock that tumbled through the dark. As it moved away from the sun, it too sped up. It defied the gravitational pull that should have slowed it down. At the time, the scientific community scrambled for a natural explanation. The most accepted theory was outgassing, or the rocket effect. Think of a comet as a dirty snowball. As it gets closer to the sun, the heat warms up the frozen gases trapped inside the rock. These gases, water vapor, carbon dioxide, or hydrogen, turn from solid ice directly into gas. This process builds up pressure until the gas bursts out through cracks in the surface. When the gas shoots out in one direction, it pushes the rock in the opposite direction. It is the same principle as letting the air out of a balloon. The balloon flies across the room because the air rushes out the back. This is a reaction force. It is a natural engine. With Oumuamua, we eventually accepted that invisible jets of hydrogen gas were likely pushing it, giving it that extra speed. It was strange because Oumuamua had no visible tail coma, but it was physically possible. Nature creates weird things, and we accepted the coincidence. But 3i Atlas is different. The comparison to Oumuamua only deepens the mystery rather than solving it. We have modelled the outgassing scenario for 3i Atlas 1,000 times. We ran simulations assuming it is made of water ice, hydrogen ice, or nitrogen. We calculated the heat from the sun and the potential pressure of the escaping gas. Here is the problem: comets are messy. When a natural comet heats up, the jets of gas erupt randomly. A pocket of ice on the north side might explode, pushing the comet south. Then, as the comet spins, that jet points in a new direction. A few hours later, a different pocket on the south side might burst. The result is usually chaotic. The comet wobbles, tumbles, and shakes. The thrust generated by the gas is wasted in different directions. It creates a net push, yes, but it is a sloppy, uneven push. 3i Atlas is not wobbling. The data shows that the extra force pushing 3i Atlas, that invisible current, is perfectly mathematically stable. The acceleration is constant. Even more terrifying, the force is aligned perfectly with its direction of travel. Imagine you're driving a car on a slippery sheet of ice. If you lose control and spids, your car moves in chaotic circles. That is a normal comet. Now imagine that same car sliding on the ice, but suddenly something pushes it from behind, perfectly straight right in the centre of the bumper, making it accelerate smoothly without spinning out. That is what is happening to 3i Atlas. For the rocket effect to work this smoothly, the gas vents on the object would have to be located exactly at the rear of the object relative to its motion, and they would have to stay there. This implies that 3i Atlas is stabilizing itself. It suggests that as it rotates, the vents somehow know to only fire when they are pointing backward. Or it implies that the object is not rotating at all but maintaining a fixed attitude, keeping its engine pointed steadily against the flow of gravity. Nature does not usually build things with such precision. In nature, randomness is the norm. A rock tumbling through space should not have a thruster perfectly aligned with its centre of mass. The odds of a random vent forming exactly at the back of the object and the object having the perfect weight distribution to prevent it from spinning are astronomical. We looked for the signature of the gas. If 3i Atlas is pushing itself with hydrogen or water vapour, our spectrometers should see the light absorbed by those molecules. We should see a cloud, a haze, a spectral fingerprint. The sensors show nothing. The space around the object is clean. There is no cloud of dust. There is no halo of gas. There is only the object moving through the void, accelerating as if it is sliding down a hill that isn't there. We are left with a disturbing list of possibilities. 1. It is releasing a type of gas we have never seen before, something that is invisible to our senses and leaves no trace. This would require a new understanding of chemistry. 2. It is not using gas at all. It is being pushed by something else. Perhaps it is reacting to the solar wind, the stream of particles from the sun, in a way we don't understand. This brings us back to the light sail theory that was proposed for Oumuamua. If the object is incredibly thin like a sheet of foil, the pressure of sunlight alone could push it. But 3i Atlas appears massive and solid on our radar, not a thin sheet. 3. The acceleration is artificial. This is the hypothesis we whisper, the one we do not write in the official reports. When a pilot flies a jet, they align the thrust with the vector of movement to gain maximum speed. They correct for drift. They stabilize the rotation. The motion of 3i Atlas bears the hallmarks of intention. The force is too clean, the alignment is too perfect. It is as if the object is riding a rail, ignoring the chaotic drag of the cosmos. As 3i Atlas dives deeper into the solar system, the invisible current is getting stronger. The deviation from the gravitational orbit is increasing by meters per second squared every day. It is correcting its course. It is not falling toward the sun anymore. It is driving toward it. We are no longer watching a rock fall through the dark, we are watching something perform a maneuver. And we are all wondering the same thing. If it can steer, where is it trying to go? We have arrived at the most controversial yet scientifically necessary part of our investigation. In the previous sections, we carefully dismantled the natural explanations. We looked at the idea of a hydrogen iceberg, a nitrogen fragment, and a dust bunny. One by one, these theories faced critical problems when tested against the laws of thermodynamics and material science. They simply could not explain how the object survived the intense heat of the sun, or why it accelerated without a visible tail. When you have exhausted every possible natural explanation, you must, as a good scientist, consider the unnatural. We must look at the possibility that Oumuamua was not a rock, but an object that was manufactured. This is known as the technological hypothesis. This is not about science fiction or sensational headlines. It is about physics. It is about looking at the data and asking what kind of object fits the numbers perfectly. The problem of propulsion. To understand why we are considering technology, we have to go back to the most stubborn fact about Oumuamua, the excess push. As the object moved away from the sun, it sped up. In space, you cannot speed up unless something pushes you. This is Isaac Newton's basic law of motion. For comets, this push comes from the rocket effect. Ice turns into gas. The gas shoots out the back and the comet moves forward. However, we saw no gas, we saw no dust. This leaves us with a physics puzzle. If there was a push but no heavy cloud of gas behind it, the exhaust must have been extremely efficient. In scientific terms, we call this high exhaust velocity. Imagine you're standing on a skateboard. If you throw a heavy bowling ball behind you, you will roll forward. This is how a normal comet works. It throws a lot of heavy gas and dust backward. But Oumuamua did not throw a bowling ball. It is more like standing on that skateboard and shining a ridiculously powerful flashlight behind you. Light has no mass, but it has momentum. If the exhaust leaves the object at the speed of light, you get a push without losing much mass at all. Nature does not typically create propulsion systems with high exhaust velocity that are invisible to our telescopes, but technology does. The solar sail concept. This line of thinking leads us to the most robust version of the technological hypothesis, the light sail or solar sail. If Oumuamua was not burning fuel to move, perhaps it was being pushed by sunlight itself. The sun emits particles of light called photons. When these photons hit an object, they bounce off, imparting a tiny, tiny push. For a heavy rock, this push is meaningless, like throwing tennis balls at a moving train. However, if the object is incredibly lightweight and has a very large surface area, that tiny push becomes significant. If Oumuamua was a thin membrane like a sheet of paper or a piece of plastic wrap, the pressure from the sun would be enough to generate the exact amount of acceleration we measured. This hypothesis solves the biggest mysteries instantly. Why no tail? Because nothing is evaporating. It is a solid surface being pushed by light. Why the tumble? If a flat, thin sheet is damaged or tumbling through space, the amount of sunlight it reflects would change dramatically, explaining the extreme brightening and dimming we observed the light curve. Why the shape? The data suggested it was either a cigar or a pancake. A light sail is effectively a flat pancake. For nature to produce a rock that is less than a millimeter thick but as wide as a football field is almost impossible. Such a rock would lack the internal strength to hold together. However, human engineers are already designing light sails exactly like this. It's a very efficient way to travel between stars because you do not need to carry heavy fuel, you just let the stars push you. If the acceleration was caused by sunlight, Oumuamua had to be artificial. The galactic parking lot, beyond the shape and the speed there, is the matter of the orbit. This is where the statistics become truly baffling. Astronomers use a concept called the local standard of rest. Think of the galaxy as a busy ocean. All the stars are like boats drifting in slightly different currents. The sun is moving, other stars are moving, and clouds of gas are moving. The local standard of rest is the average speed of all the stars in our neighborhood. It is like the still point of our region of the galaxy. Most objects we see are moving relative to the still point. They are participating in the galactic dance. Oumuamua was different. Before it entered our solar system, it was at rest relative to the local standard of rest. It was sitting perfectly still in the galactic parking lot. It was not moving, we hit it. Our solar system moving through the galaxy smashed into this object like a windshield hitting a bug. Why is this important? Because being at rest in the local standard of rest is a very rare state for a random rock. Only 1 in 500 stars is this still. The statistical probability of a random rock ejected from another star system just happening to sit at that exact velocity is astronomical. Furthermore, the specific orientation of its arrival was unique. It came from a direction that minimized the chances of it interacting with anything. When you combine the unique velocity sitting still in the galaxy with the unique shape extreme aspect ratio and the unique acceleration non-gravitational push, without gas, the odds of this being a coincidence drop to 0. Some researchers have calculated the probability of a natural object having all these traits as being roughly 1 in 100 million. In science, when the odds are 1 in 100 million, you are usually looking at the wrong theory. You need a new theory. Space junk or a probe? If we accept the possibility that it is technological, does that mean it was a spaceship piloted by little green men? Not at all. That is a leap we do not need to make. A more grounded perspective is that of space archaeology. Humans have sent 5 objects into interstellar space. Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, and New Horizons. In a million years, these will just be dead pieces of metal floating in the void. Oumuamua could be the same thing. It could be a buoy, a navigation marker left in the parking lot of the galaxy, a fragment, a broken piece of a larger Dyson sphere or communication array, space trash, a discarded solar cell from a civilization that launched it 1 billion years ago. The fact that it tumbled suggests it was not functional and it wasn't scanning us. It was likely dead tumbling debris, but even space trash implies a civilization that created it, expanding the scientific mind. The resistance to this hypothesis is often emotional, not logical. We are terrified of the giggle factor. Scientists worry that if they say the word alien or technology, they will be ridiculed or lose their funding. So they prefer to invent invisible hydrogen icebergs, rather than admit that the data looks artificial. But true science requires humility. We must follow the evidence wherever it leads, even if it leads to a conclusion that changes our place in the universe. Galileo was persecuted for saying the Earth moved around the Sun. Today we face a similar psychological barrier. We want to believe we are special, or at least that the universe is dead and quiet. Oumuamua challenged that silence. If it was a rock that acted like a machine. If it was a machine, it implies we are not alone. Both possibilities are frightening, but only one fits the data without breaking the laws of physics. The technological hypothesis does not require us to invent new types of matter like solid hydrogen. It only requires us to admit that perhaps, just perhaps, someone else built a sail to catch the wind of the stars. As the calendar pages turned toward the end of the year, the atmosphere on Earth began to shift. We were no longer just reacting to a discovery. We were preparing for a meeting. The date was circled on digital calendars and written in notebooks across every continent, December 19th, 25. This was the date of the closest approach. This was the moment when the traveller from the dark, the asteroid that had captivated our imagination, would brush past our home. It would not hit us. The mathematics of the trajectory were solid, checked and rechecked 1,000 times by the brightest minds from Paris to Beijing. It would pass safely, but in cosmic terms it would be a whisper away. For the scientific community, this was not just an event. It was the Super Bowl, the World Cup, and a grand symphony all rolled into one. The preparation was meticulous, required a level of patience that is rare in our modern world of instant gratification. Science cannot be rushed. It is a slow, deliberate art of waiting for the universe to reveal itself. High above our heads, the big guns were turning their attention. The James Webb Space Telescope, sitting at its lonely outpost 1 million miles from Earth, received its commands. Webb is a time machine and a heat seeker. It looks at the universe in infrared light, which is essentially looking at heat. Its job was to stare through any dust or gas surrounding the asteroid and look at the surface itself. The scientists wanted to know, is it warm, is it radiating energy? What is the texture of this ancient rock? Closer to home, the Hubble Space Telescope, the old and faithful grandfather of space observation, swiveled its mirrors. Even after decades of service, Hubble remained our best eye for visible light, the same light our human eyes can see. While Webb painted a picture of heat, Hubble would paint a portrait of colour and shadow. Together, they would create a composite image more detailed than anything we had ever seen before. But the network extended far beyond the salience of SES. On the ground, the great radio telescopes began their work. These are not telescopes that look with glass lenses. They are giant ears. They look like massive satellite dishes, bowl-shaped structures pointing at the sky. They were preparing to send powerful radio waves out into the blackness. These waves would travel at the speed of light, hit the surface of the asteroid and bounce back to Earth. By measuring how long the echo took to return and how the signal changed, scientists could build a 3D shape of the object. It is like a bat using sonar to see in the dark, but on a planetary scale. This method allows us to see every mountain, every valley and every crater on the asteroid, even though it is millions of kilometers away. Further out in the solar system, the JUICE spacecraft launched by the European Space Agency to explore Jupiter was also part of the conversation. Though it was millions of kilometers away on its own journey, its sensors contributed to the data profile of the background environment. It felt as though every machine humanity had ever built was waking up to watch the show. However, the true beauty of the global eye was not found in the billion-dollar control rooms of NASA or ESA. It was found in the backyards. Thousands of amateur astronomers were polishing their lenses. These were not professionals. They were teachers, bus drivers, retired nurses and high school students. They stood on rooftops in Tokyo, in open fields in Australia, and on snowy driveways in Canada. They communicated through online forums sharing coordinates and weather reports. Clear skies in Chile. One would type, "Cloudy in London, relying on you," another would reply. It was a relay race of observation. As the sun rose in one part of the world, blinding the telescopes there, the sun set in another part, opening the night sky for a new shift of watchers. The asteroid could never hide. It was being watched 24 hours a day by a network made of human passion. This created a profound sense of connection. For a few weeks leading up to December 19th, the usual noise of the world seemed to quiet down. The arguments about borders, politics, and economics did not vanish, but they felt smaller. When you look up at something so old and so vast, the lines drawn on maps become invisible. We were reminded that we are all standing on the same small blue marble. We are all clinging to the same rock as it spins through the void. The asteroid was an outsider, a visitor, and its presence made us realize who we are. We are the people of Earth. The tools we use to understand the universe are extensions of our senses. The telescope is a larger eye, the radio dish is a larger ear, the spectrometer is a way to taste the chemistry of the stars. We use these tools because we are curious. We want to know our place in the story. As the date of December 19th approached, a feeling of serenity settled over the observatories. The chaotic panic of the early days was gone. In its place was a quiet, studious hope. The scientists monitored the data streams with a rhythm that felt like a heartbeat. They watched the numbers on their screens, distance, decreasing velocity, constant rotation, steady. 10 million kilometers, 5 million kilometers, 2 million kilometers. The asteroid grew brighter in the lenses. To the naked eye, it was still just a faint star moving slightly faster than the others. But to the global eye, it was a world of its own. We could see its ridges and its dark spots. We could see where it had been battered by collisions billions of years ago. This was the patience of science rewarded. We did not shoot at it. We did not try to blow it up or divert it. We simply watched. We listened. We learned. On the night of the closest approach, the data centers were quiet, filled only with the hum of cooling fans and the soft clicking of keyboards. Coffee cups sat steaming on desks. People spoke in whispers, not out of fear, but out of reverence. We were about to have a close encounter with history. The universe was passing by our window, and for the first time all of humanity was awake to wave back. The silence between expectation and reality. There is a very specific quiet moment that happens in the life of every scientist. It is a moment of silence that sits between what we expect to see and what we actually see. Imagine you have a map of a forest. You have used this map for 20 years. It tells you exactly where the river bends, where the tall oak trees stand, and how to get from the entrance to the exit. But one day you go for a walk with your map, and right where the paper says there should be a flat, grassy field, and you find a deep, dark lake. Your first reaction is usually not excitement, it is annoyance. You might tap your compass and you might clean your glasses. You think, I must be reading this wrong, or the map maker made a mistake. You might even feel a little angry. This is human nature. We love patterns. We feel safe when the world behaves exactly how our textbooks say it should. We want the universe to be predictable. But this frustration is actually the most beautiful part of science. This is the moment where the data does not fit the model. If every experiment gave us exactly the result we expected, science would be dead. We would just be confirming what we already know over and over again. When the data refuses to cooperate, when the numbers go up instead of down, the universe is trying to tell us a secret. It is whispering, you are looking at this the wrong way. The danger of expectative. In school, getting the wrong answer is a bad thing. If you write that 2 + 2 = 5, you get a red mark on your paper. We are trained to believe that being correct is the goal. But in the study of the cosmos, being wrong or being surprised is the only way we learn anything new. As scientists get older and become experts, they often lose the ability to be surprised. They build a reputation. They have awards and degrees on their walls. They have a status to protect. When an expert sees something that does not fit their theory, their instinct is often to force it into a box they already understand. If they see a strange light in the sky, they say, it is probably just a glitch in the telescope. If they see a particle moving strangely, they say, it is just an error in the calculation. This is where the physicist Avi Loeb challenges us. He warns that this attitude is dangerous. When we refuse to look at weird data because it sounds crazy or impossible, we are like a horse wearing blinders. We only see the road ahead that we have already built. We do not see the vast fields on either side. The lesson of the child: stay curious. Avi Loeb suggests that the ideal scientist should think like a child. Think about how a child explores a beach. When a child picks up a strange shell or a smooth piece of glass, they do not care if it is valuable. They do not care if it fits into a specific category in a biology book. They do not worry if their friends will laugh at them for picking it up. They just look at it. They turn it over in their hands. They ask, "What is this?" This is the essence of the phrase "stay curious." Loeb uses the example of Oumuamua. In the year 2017, an object from outside our solar system passed near Earth. It was the first visitor we had ever seen from deep space. It did not look like a normal rock. It was long and flat. It moved in a way that gravity alone could not explain, as if something was pushing it. Many scientists tried very hard to explain it as a normal comet or asteroid, even though the data did not match perfectly. They were afraid to suggest it might be something else, perhaps something artificial, because that sounds like science fiction. Loeb argues that we must be brave enough to consider all possibilities, even the ones that make us uncomfortable. We must be willing to look at the object and say, maybe this is something we have never seen before. To be truly scientific is to be vulnerable. It means standing in front of the unknown and saying, "I do not know what this is, and that is wonderful." The universe has no obligation to you. There is a hard truth that we must accept to find peace in science. The universe is under no obligation to make sense to you. For thousands of years, humans believed we were the center of everything. We thought the sun revolved around the earth. We thought the stars were just little lights painted on a ceiling for our amusement. Even today, deep down, we subconsciously believe that the laws of physics were made for us to understand. We want the universe to be logical in a human way. But the universe is ancient. It has been here for nearly 14 billion years. It will be here long after we are gone. It is vast, cold, violent, and beautiful. It creates black holes where time stops. It expands at a rate that is faster than the speed of light. It contains mysteries like quantum entanglement, where two particles can communicate instantly across the universe, defying our common sense of space and time. When we encounter something that seems impossible, we should not be offended. We should be humbled. The universe is the master. We are the students. We cannot demand that the universe follows our rules. We must change our rules to follow the universe, embracing the dark and the unknown. There is a great sense of relaxation in this humility. It takes the pressure off. We do not need to have all the answers right now. In our modern world, we are obsessed with certainty. We want to know exactly what the weather will be tomorrow. We want to know exactly how the stock market will move, but science teaches us to be comfortable with uncertainty. Consider the concept of dark matter. When astronomers look at a galaxy, they measure the mass of all the stars and gas they can see. Let us say that mass equals 1 million units. But when they measure how fast the galaxy is spinning, the math says there must be 5 million units of mass holding it together. There is a huge gap. The data does not match the model. Instead of giving up, scientists admit, there is something else here. We cannot see it. We cannot touch it. We do not know what it is made of, but it is real. We call it dark matter, but that is just a fancy name for we do not know yet. And that is okay. Living with that mystery is what drives us forward. If we knew everything, there would be no reason to wake up in the morning and look through the telescope. The mystery is the fuel for our imagination. Walking with humility. So how do we apply this philosophy to our own lives? It means listening more than we speak. When someone presents an idea that contradicts what we believe, our first reaction should not be to attack it. We should not say that is impossible. Instead, we should channel our inner child. We should ask, why? What evidence do you have? Show me. It means realizing that our knowledge is like a small island in a giant ocean of ignorance. As we learn more, the island grows larger. But as the island grows, the shoreline, the border where the land meets the water, also gets longer. The more we know, the more we realize how much we still have to learn. This is not a sad realization. It is a liberating one. It connects us to the generations of curious humans who came before us and the generations who will come after us. We're all just walking along the beach together, picking up shells, trying to understand the vast ocean before us. The moment the data does not fit the model is not a failure. It is an invitation. It is an invitation to let go of our ego, to open our minds, and to let the universe show us something we never dared to imagine. And so the curtain begins to fall on this brief, magnificent drama. The bright spark that we watched with such curiosity has now faded into the deep velvet backdrop of the night sky. We have reached the end of the chapter, the final page of the story where the protagonist walks away from the camera, growing smaller and smaller until they are nothing more than a speck against the horizon. The noise of the data analysis has stopped. The arguments among the scientists have quieted down. The telescopes are turning to look at new things. But out there in the cold emptiness, the journey of this mysterious object continues in absolute silence. It is time for us to take a deep breath and let go. As we watch it disappear, We must return to the question that started it all, though the answer no longer seems to matter as much as it once did. Was it a piece of rock frozen and ancient chipped off a dying planet billions of years ago? Or was it a ship, a machine built by hands? We will never shake sent to see if anyone was home. In these final moments, as the distance between us grows by thousands of miles, every second the distinction blurs. If it was a rock, it was a noble one. It carried the history of a star system we will never see. It survived the crushing gravity of the void and the freezing temperatures of interstellar space to bring us a moment of wonder. If it was a ship, it was a silent observer. It did not ask for our radio waves. It did not ask for our permission. It simply glided through our backyard, took a look at our sun, and decided to keep moving. Whether it was born from nature or built by intelligence, it was a messenger. It told us that the universe is bigger, stranger, and more beautiful than we can keep inside our textbooks. It reminded us that we are not alone in the dark. We are surrounded by drifting history. Think back to when it was closest to the sun. It moved with such incredible speed, faster than anything we could ever hope to build. It felt the searing heat of our star. It felt the heavy hand of gravity trying to pull it in, trying to trap it here with us. But it was too fast, too free. It used that energy not to stay, but to fling itself back out into the freedom of the dark. It danced with the fire and survived. Now that heat is just a memory. The warmth it absorbed is leaking away into the vacuum. It is cooling down, returning to the frozen state it has known for eons. The journey ahead for this traveller is long, so long that our human minds struggle to understand it. It is leaving the neighbourhood. Soon it will pass the orbit of Mars, then the giant realm of Jupiter. It will slip past the icy rings of Saturn and the dark, windy worlds of the outer rim. And then it will cross the invisible line where our sun's wind stops blowing. It will enter the true ocean of the universe. Ocean. There is a profound peace in that thought. Imagine the silence out there. It is a silence deeper than the bottom of the ocean, deeper than the quietest cave. There is no air to carry a sound, there is no wind to rustle, there is only the perfect, unbroken stillness. The object will tumble slowly end over end in a rhythm that will not change for millions of years. It is a ballet with no audience, performed on a stage that has no edges. As it drifts away, the sun will become just another bright star in its sky, indistinguishable from the millions of others. The Earth, our chaotic, loud, beautiful blue home, will vanish from its view completely. We become invisible to it. The arguments, the borders, the noise of our civilization, none of that reaches it anymore. It is free from us. It is free from everything. We should send it off with a sense of gratitude. It gave us a reason to look up. For a few short months we stopped looking at our feet and looked at the heavens. We wondered. We dreamed. We asked, what if? It expanded our imagination, stretching it across the galaxy. Now we must let it sleep. The path it travels now is the endless journey. It is a path without a map. It might drift for another billion years before it sees another star up close. It might travel through clouds of cosmic dust or slip silently through the darkness between galaxies. It has no deadline. It has no schedule. It has all the time that exists. So let us lower our voices. Let the night wrap around the world. Imagine you are floating beside it, watching the stars slide by. Oh, the urgency is gone. The mission is complete. Good night, wanderer. Good night, mystery. Sleep well in the arms of the great void. Let the gravity of the Milky Way gently guide you. May your path be clear of debris. May you carry the memory of our sun's warmth in your heart even as the ice takes over again. You are a child of the universe returning to the nursery of the stars. We remain here anchored to our rocks spinning around our fire. But a part of us goes with you, a part of our curiosity. Our spirit of exploration drifts along in your wake. You have linked us to the vast unknown. The darkness is not scary, it is peaceful. It is a velvet blanket pulled up tight. The stars are the nightlights left on to keep you company. Go gently into that good night. Float on the river of forever. Goodbye, Atlas. Goodbye, strange visitor. The show is over, the lights are out, and the galaxy is quiet. Rest now. Rest in the beautiful endless dark.